I'm here today to talk about point clouds and what information we can generate from point cloud data. During the abstract that I wrote for this presentation, I said that point clouds are becoming ubiquitous in AC projects. And my first reason to say that is in our business, we're producing point clouds during the past years, and the volume of point clouds that we're producing is increasing with every year. Search engine data is also showing that interest in point clouds is increasing. At the same time, we have professional bodies creating guidance notes for point clouds and surveys. We also see market research highlighting that the market for LiDAR information, LiDAR devices, is going to increase over 17% over the next 5 years. So those are all indicators that the market for point clouds and spatial information within the industry is increasing. Simultaneously, we're also seeing that there's been new concepts that have emerged during the past few years. We hear about scan to BIM, so measuring an existing structure and transforming that information into BIM information. Scan versus BIM, that relates to the process of using point cloud data during construction to perform clash detection, site validation, and those tasks. And we also hear about digital twin, so ensuring that we have a digital representation that relates to existing structures, and then we can follow up to indoor navigation applications, robotics, you name it. But what is a point cloud? It's a 3D digital representation of the built environment, of an object. It's essentially a list of X, Y, Z coordinates, but it can also have additional information that most people haven't really heard about. Color, of course, if we use a digital camera, it can include that information within the point cloud file. If we use a LiDAR device, we can include intensity information, which essentially relates to the amount of energy that returns to the sensor. And those two components, they're really there to assist the human eye. They're not computationally important per se, but they help us interpret the point cloud data. Further to that, we can also include normal information, which gives us information on the spatial relationship between points. If we use an aerial LiDAR system, it will also include the type of return, whether it's the tree or with the ground that hits the coordinate. In terms of file formats, there's not one single format that is accepted by all vendors. Some software vendors have their own proprietary file systems, but there's a few open formats that can be used to exchange information between softwares. I have listed there the PCD format, which is developed by the Point Cloud library, and also the E57 file format, which is at the moment the most popular file to exchange point cloud information. A little bit of time dedicated to the measurement devices. One of the most popular devices these days is the laser scanner, but there's different types of laser scanners, different price ranges, different accuracies, and the price is really related to the physical components that go into the laser scanner. They start at the price range of 10,000 euros probably, and they go up to the survey grade laser scanners that will cost almost 100,000 euros. But the components that go into them, they're not really the same, and the accuracy varies. So the cheaper laser scanners can probably give you measurements up to 20, 30 millimeter accuracy. And then when we go up to the survey grade laser scanners, the accuracy can be within the millimeter range. There's equipment that is set up like a traditional survey tool on a tripod, but there's also handheld devices like this one, which explore simultaneous location and mapping techniques to dynamically capture survey information. there's scanners that can be mounted on vehicles, and those are useful to survey roads, railways, for example. But there's also 3D cameras that just use a combination of lasers and images to capture 3D information. And like Gerrit was saying, UAVs are also a survey tool these days. The UAVs are mounted with a camera that captures a lot of digital photography of the environment. With that digital photography, we can apply photogrammetry techniques, structured from motion techniques, and the output of that is a point cloud. So essentially, point clouds are rich 3D information of the built environment. They can be used to document from above and from within buildings as well. They are the most efficient method to capture information on a building. One of the bottlenecks of using point cloud data is the volume of data that we can end up with. In large projects where we're going to use, we're going to capture a lot of information, they can really scale up to hundreds of gigabytes and be somewhat difficult to use if you don't have a powerful machine and hardware. In this particular project, we scanned over 500 times, and we ended up with 19 billion points and a database size of 700 gigabytes. They can be very heavy. What I'm here today is to talk about what the point cloud can provide, what additional information can we extract from the point cloud, and how we can manage that data. One of the almost immediate deliverables from point clouds is an old mapping technique that we can apply to check, to verify height variations. So providing we use a survey-grade laser scanner that compensates for tilts, we can use that information to check floor flatness, for example, or the verticality of walls. And this is just done by applying a color-coded scheme to a point cloud. That's essentially a useful deliverable that most people don't consider, and that can be used without too much interference and too much modeling of the point cloud. Another almost direct output from the point cloud is a triangulated surface. It is essentially a surface model that is created from the point cloud. It's very, very valuable in terms of visual information. However, it can be very computational, heavy computationally. So it doesn't really, it's not efficient if we have a large structure. It only works for smaller point clouds. So where do we go from there? What can we do with point clouds to provide information to architects and engineers? The traditional workflow is there listed as a manual workflow where we capture the point cloud data, and then following a processing stage where we register and filter the data, we start drafting or modeling, usually done by hand. So there is an operator that reads the point cloud and creates line work or 3D models manually from the point cloud. The workflow listed below is a more unambiguous workflow where we use point clouds data, the same point cloud data, but then we apply a feature extraction step in between, and we automate the drafting and modeling using computer instructions. I have it there listed unambiguous in inverted commas because we also need to factor in the measurement errors that every device has built in. And of course, if we use statistics, we also have to consider the residuals that will be present in any case. Often I hear that the results from point clouds, the models and drawings are an interpretation, but they don't have to be. We can use computer tools to obtain accurate models from point clouds. We can, for example, fit objects onto the data set. There's numerous plugins, software plugins, that allow us to model pipes, steel sections, and walls and columns, for example. So there's no ambiguity there. Another possibility is to use region growing techniques, where given a set of constraints, normally angle and distances, we can, given a starting point, extract and isolate the planes or the pipes. It's not very visible in this image, but given a starting point on that pipe, we can isolate the point cloud that relates to this regular pipe run. What is actually happening in the background? It's just a regression technique. Some of the plugins have linear regression, but we can also use nonlinear regression. Ransack is one of the known algorithms for that. Essentially, it removes outliers in the iterative process and allows us to actually obtain a more relevant data set that will sort of exclude any spurious data that might be in the photo. If we use this method, then we can fit geometric primitives. Objects that are computationally and mathematically well represented, it can be detected from the point cloud quite easily. In this little image there, we see some shapes that can be extracted: plane, spheres, cylinder, cuboids. All of those can be detected within the point cloud, and we can isolate areas of the point cloud that describe that sort of shape. So the workflow to model can be something like this. It's borrowed from the point cloud's library website, and describes that given the initial point cloud, we can apply filtering algorithms and segment that data given the geometry of the data. And once we have that, it's computationally straightforward to reconstruct and fit models onto the point cloud with limited human intervention. What's the point of doing that? The point is to automate modeling tasks, use the data itself, use computer instructions to take the data set and create models automatically, or with limited human input, and thus less ambiguity in the model. That works very well if the structure is regular, but in our business, we often need to measure buildings that are 50, 60-year-old, maybe more, and we find that sometimes the scenes we see on site are somewhat chaotic. There is no flat walls, there is insulation material in the pipes, there is data voids in the point cloud caused by objects that are present there that create shadows. So the point cloud data is sometimes, or I would say often, incomplete. So using regression techniques to fit regular objects onto a wall that is not straight, it's not going to work. So this ends up being a very manual and tedious process, and costly as well. But there's ways around that. If we don't use regression techniques, we can convert the point cloud into voxel grids, which is essentially a little set of tiny cubes built around the point cloud. Each of those cubes has a central point that describes the point cloud. And once we have this sort of representation, we can use convex and concave criteria to partition the point cloud, classify the point cloud, and essentially isolate irregular objects on the point cloud. In practice, we're going to segment the point cloud using the geometry of the point cloud into regions, and take those regions to automate the modeling tasks that we're not going to be able to do with regular regression techniques. This image here shows a little cube size of 2 millimeters. The grid resolution in this case is 200 millimeters. And you can sort of see what that means in terms of spatial terms. This is the grid that is created. Here we have that normal information that I was talking about earlier. Essentially, the normal establishes the origin of the measurement and how each measurement relates to the nearby measurements. So using that, we know that this measurement comes from up, and in here it comes from below. And essentially, it allows us to segment point cloud into regions. Of course, that we're using a grid resolution which is not very detailed. So we're going to be missing, we're going to group objects into objects that are not really meaningful. So we're probably going to have to end up with a smaller resolution that will be able to pick up finer detail. In this case, we have a voxel size of 1 millimeter and a grid resolution of 20 millimeters, so quite small. And we can see that it results in a proper classification of objects. So we see that here that the insulation material is being segmented somewhat correctly. Each object is showing up as an individual component. So something that is in the point cloud, we can obtain from the point cloud by using voxel grids and concave and convex criteria. What is the purpose of doing that? The purpose is to automate the modeling process. So this information, this classification information, can be stored into a point cloud file. We can use conditions and parameters that are programmed and automate the modeling tasks and end up with a model that is detailed, unambiguous, and represents closely the site conditions. As a member of an organization that produces point clouds, it's in my interest to highlight the benefits of using them in your day-to-day business. Point clouds are definitely the most comprehensive method of capturing site information. At the same time, we usually have reliable accuracy statements that relate to the equipment that we use and how we assembled the point cloud. Using point clouds definitely improves collaboration amongst team members. We can have the engineers and the architects working from the same data set and making sure that everything is coordinated, given that the base information is the same. It reduces risks on projects. We've heard about scan to BIM, scan versus BIM. I'm going to introduce here a new concept that we probably heard before, scan to BIM to field. So during the construction process, we can use point clouds to design and then take that design to site and verify the built construction with the point cloud information that we can capture after it is built. As I said before, it facilitates compliance control, so we can verify the design versus the as built. And all of this means that it is going to save costs and time. That's it. Hopefully, I've showed a few more things that we can do with point clouds.